Welcome back, y'all. In this video, I'll be making m-nitrobenzoic acid, or meta-nitrobenzoic acid, in 3 ways. The first way gives the purest acid, the second and third give mostly the meta-isomer, some ortho, and trace amounts of the para-acid. I don't know if I need pure meta-acid for what I intend to use it for, as I don't know if it'll even work, but I thought I'd try the method that yields the purest product in case it does. In my quinacridone synthesis series, one of the steps is oxidizing dihydroquinacridone to quinacridone. I used nitrobenzene in the previous video, but I don't have enough nitrobenzene to conveniently oxidize a large amount of dihydroquinacridone that I'll have. There are other methods to oxidize it, however, like chloranil. I could make some and use it, and I might, depending how what I have planned goes, but we'll see. One method that I thought I would try was with sodium metanitrobenzene sulfonate. I misremembered it as sodium m-nitrobenzoate and didn't realize it until after I spent a few hours looking into the various syntheses of it. When I did realize it and looked up how to make the sulfonate, the method is by sulfonating nitrobenzene with oleum. It might seem odd to use a compound that's made using nitrobenzene, which is proven to work. Why, if you already have nitrobenzene, would you do this? Because the procedure with the sulfonate uses proportionately a lot less compared to the one using nitrobenzene. Nitrobenzene is used in a large excess, as it also serves as the solvent, whereas with the sulfonate, the solvent is a mixture of water and ethylene glycol. The downside to this is the sulfonate itself, or so I thought initially. I don't like working with oleum in my home lab. If this were done in a professional lab setting, in which I actually have worked with oleum in research, I'd be fine with it, but I don't have the safety precautions that I would have in a professional lab setting that I would feel comfortable working with at home. Typing this script, I confess that I am a big dummy, as I just looked it up, and I can buy sodium metanitrobenzoate on Amazon. I didn't think of looking it up until now. Some chemicals are more obscure and or have niche uses, so I don't even bother looking them up on Amazon, eBay, or other chemical supply websites. And now I feel dumb. Too late now though, kind of. I ordered some, since it's only $20 for 500 grams of it, so it should be coming in the next day or two. In the meantime, I'll do what I plan to do, which is try using the metanitrobenzoic acid in the same way as the sulfonate and see if it works. I doubt it, but it's worth trying, and if it doesn't work, I do have another use for the acid. Nitrobenzoic acids readily decarboxylate at fairly low temperatures, the meta-isomer at 238 degrees, the ortho-isomer at 180 degrees, and the para-isomer somewhere above 240 degrees. The para-isomer actually sublimates before it can decompose, so it's good that very little is produced in this reaction. These temperatures are easily achievable in an ordinary glass distillation setup, so I think this is a viable route to nitrobenzene, starting from the very cheap sodium benzoate. I know that nitrobenzene can be made by the mixed acid nitration of benzene, which is how I made it for the stuff that I used in scrap synthesis video, and left over from that synthesis is what I used in my last video. And benzene can be made by the decarboxylation of sodium benzoate by fusing it with sodium hydroxide in a paint can connected to a distillation setup, and the yield is usually about 70% from what I've seen, and about 80 to 85% for the nitration. So I'm curious about which is more efficient, and not having to work with a paint can setup is better than having to use it. On to the video. Method 1 is the roundabout high meta-isomer yielding process. First, benzoic acid and methanol are converted to methyl benzoate by Fischer-Speier esterification with sulfuric acid as the catalyst. Then, methyl benzoate is nitrated. Compared to the nitration of benzoic acid, nitrating methyl benzoate yields very little of the ortho and para isomers and mostly the meta-isomer. Nitrating benzoic acid produces this ratio of the isomers. After the nitration, the ester is saponified to the sodium salt, which is acidified to give the free acid. Methyl benzoate has a density of 1.0837 grams per milliliter, fairly close to that of water, so they don't separate as sharply as is ideal. To get a better separation, carbon tetrachloride is added to increase the density of the organic layer. Using a scale to weigh the crude organic layer was pretty pointless since I used a little more carbon tet to rinse out all the glassware. I dried the mixture with anhydrous magnesium sulfate, then filtered it through cotton and distilled it. I ended up with 105.8 grams of methyl benzoate, which is an 82.52% yield. The literature yield was 92%, and I even refluxed it for twice as long as it said to get a higher yield, but mine was still lower for some reason. Now, time to nitrate the ester. I completely fucked this up the first 2 times because of something that's mostly not my fault. I don't do nitrations often, so I was very confused as to why it sucked so bad. The procedure I used was from Vogel's textbook of Practical Organic Chemistry. Both the 3rd and 5th editions of the book have the same missing reagent in this procedure. In the Orgson procedure that Vogel scaled down and put in his textbook, the ester is firstly dissolved in sulfuric acid, then the mixed acid is gradually added to it. This addition involves a lot of heat, which is why it's cooled in an ice bath and takes at least an hour. The first sign that something went wrong was when barely any heat was evolved while adding the mixed acid. It barely took 10 minutes while maintaining the temperature between 5 and 15 degrees. After the acid was added and the mixture was stirred for an additional 15 minutes, it was poured into approximately 700 grams of ice. This was the second sign that something went wrong. Why was there so much ice required when so little melted upon adding the reaction mixture? The third sign was when no solid precipitated, and I was able to use a separatory funnel to separate the 2 layers. Essentially, the acid dissolved in the unreacted methyl benzoate. Adding ice-cold methanol did cause a solid to precipitate, which I filtered off, but there wasn't nearly as much as there should have been. I boiled down the methanolic filtrate and redid the reaction, scaled down to the amount of unreacted ester. Same thing happened, and I got even less product. When boiling off the methanolic filtrate the second time, I let it go too long and definitely lost some methyl benzoate this way. After looking into it and realizing how I fucked up, I set it up for the third time the correct way. Same as before, and the mixed acid addition took about an hour and 20 minutes. Adding the reaction mixture to ice finally worked the way it should have this time. So the procedures in Vogel's textbooks just straight up left out the sulfuric acid that you're supposed to dissolve the ester in. I filtered off the solid that precipitated, washed it with water, and transferred the solid to a beaker with some ice-cold methanol in it again. The ice-cold methanol serves to remove any of the ortho and para isomers. I continued my biffing and knocked the stupid beaker over when I was going to filter it, so I lost even more product in yet another dumb way. After filtering off what I didn't spill and air drying, here are my 3 crops. The total 67.7 grams represents a yield of 48%, which sucks ass compared to the 81 to 85% literature yield, and is even worse for reasons I'll talk about later when it comes to the analysis of all the products. I could have recrystallized the product, but my yield was already terrible enough, so I didn't. Further, the saponification procedure is also from Orgson and references the previous procedure, saying recrystallization isn't necessary. The saponification is simple. It's done by boiling the methyl m-nitrobenzoate with an aqueous solution of sodium hydroxide for about 5 to 10 minutes, allowing it to cool, then diluting it with water to twice its volume. The resulting solution is poured into a slight excess of concentrated hydrochloric acid, and I used the molar equivalent of 10 molar hardware store hydrochloric acid. It's important to add the sodium salt solution to the acid, and not the acid to the sodium salt solution, because apparently if you do, a less soluble acid salt separates that can't be completely removed from the m-nitrobenzoic acid. The acid is filtered off and washed with water. I decided to demonstrate how differences in rates of cooling of solutions in recrystallization affects the crystal formation. Fast cooling gives smaller crystals, slow cooling gives larger crystals. If I hadn't already lost so much product over the course of the reactions up until now, I would have filtered the solutions hot because they weren't clear, since that bothers me. I was too resigned at this point to do it. Next, a direct nitration of benzoic acid. I used the same nitration procedure as I did with methyl benzoate, just with benzoic acid instead. I think benzoic acid is a little more deactivated towards aromatic electrophilic substitution than methyl benzoate, so rather than keeping the temperature between 5 and 15 degrees, I didn't let it go above 25 degrees during the addition of the mixed acid, which took about 2.5 hours, and then I heated up the ice bath to make it a hot water bath until the reaction mixture became clear, which was at about 60 degrees. After letting it cool, I poured it into ice like before. I used this glass pot since I don't have a beaker big enough. I filtered it in 3 batches since I don't have a filtering flask or funnel big enough. I transferred the combined crude acid crops to the same pot as before, added some water to it, boiled it, let it cool, and filtered it again. This wasn't a recrystallization, as I'd need like 4 liters of water for this much acid. Rather, it's a way to both remove the residual dilute acid and stuff adhering to the paste, and in the process, significantly reduce the volume. This is very apparent by all of the solid fitting in this funnel. I did have to empty the filtering flask, since I wanted to wash the solid with water, but at least I didn't have to empty the funnel. I transferred the product to this ceramic dish and put it in front of my space heater until it dried. Once dry, I put the dish on a hot plate and cranked the heat all the way up to melt it. This is to remove water, if present, and anything else volatile. Lastly, a direct nitration of benzoic acid with a twist. This procedure is very old, from 1877. More about that in the video description. I like the 1877 paper's method, not just because it's old, it also doesn't even use free nitric acid, it uses potassium nitrate. The nitric acid is formed in situ with this method. The benzoic acid and potassium nitrate are powdered and thoroughly combined with a mortar and pestle. This mixture is gradually added to the sulfuric acid while stirring. I add it at such a rate that the temperature stays around 50 to 60 degrees. Once all of it's added, I crank the heat up on the hot plate, but the water doesn't get hot enough for the mixture to become clear, so I move it to a heating mantle. The procedure says to heat the mixture until an oily layer forms on top, so I did that. I left the funnel on and stoppered the other necks because I figured it would reflux and the rest of the benzoic acid and potassium nitrate mixture adhering to the funnel would drip down and my mechanical loss would be minimized. This worked, and of course a lot of nitrogen dioxide gas was evolved as it was heated. I waited for it to cool and the top layer of nitrobenzoic acid solidified, sealing in the bottom layer of some combination of sulfuric acid, nitric acid, potassium bisulfate, and maybe potassium sulfate. I had to reheat it up to be able to pour it onto the ice, and I just used the amount of ice that would fit in a 1-liter beaker. Not nearly as much heat was evolved as when the previous reaction mixtures were poured onto the ice, so I had to heat it up on a hot plate. Once the ice was melted, I filtered it, washed the acid with water, and did the same non-recrystallizing boiling with water as I did in the previous nitration. Once cooled, I filtered it, washed it with more water, and melted it like before. Once the residual water boiled off, the temperature rose to, like 170 degrees, 180 degrees, and I took it off the heat to solidify. Here's a breakdown of all the reactions and their yields. Obviously, the first run sucked for the reasons you saw, but after checking the melting points of both crops of crystals from the recrystallization, I found another one. Even with the temperature control, some dinitration occurred since such an excess of nitrating acid was used, so my product is contaminated with dinitrobenzoic acid. The products didn't fully melt at m-nitrobenzoic acid's melting point, but they did at 3,5-dinitrobenzoic acid's melting point. This explains why not all of the acid dissolved when I was trying to recrystallize it. I'm definitely going to just wait until my sodium metanitrobenzene sulfonate comes in the mail, instead of doing what I said in the intro, which was using the metanitrobenzoic acid in place of it for the dihydroquinacridone oxidation. I might use some of what I made in the second or third run for that, but I don't know yet. Still thinking about it. It does suck how the first run turned out, but oh well. That's chemistry, I guess. Anyway, about the second and third runs. I'm super happy with them. Because I didn't care about separating the isomers produced, I don't have a sure way to check the purity of either products other than the gain in weight and the slight color change. I have an explanation for why the melting points wouldn't serve as an accurate indicator of purity in the description. That also kind of contradicts the nitro versus dinitrobenzoic acids differentiation that I just talked about. This video was long enough though, so I'm going to call it there. The next video will probably be about the decarboxylation of these acids. I might do a smaller scale, proper version of the first run to make up for just how shitty I did. I'm kind of burnt out on this nitration reaction though, so if I do, it won't be for a little bit. And that's about all I've got. Thanks for watching. If you enjoyed the video, like, comment, share, and/or subscribe. I really appreciate it. It helps me out, and I will see you in the next video.